Thank you for the introduction. I'm Taehyung Lee from Sungkyunkwan University, and this is joint work with Virginia Tech and Igalia. And today I'm going to talk about a page management scheme for tiered memory systems called MEMTIS. In recent years, alongside the traditional DRAM, new memory devices like CXL memory expander are very actively developed and explored. DRAM offers very fast load and access latencies, but it tends to be expensive and it provides relatively low capacity. On the contrary, CXL memory expander and Intel Optane memory solution provide a vast amount of memory capacity with more cheap prices. However, they also come with the trade-off of slower performance. So the tiering both types of memory devices is one of the promising solutions to strike a balance between the strengths of both of them, and thereby creating cost-effective and flexible memory systems. In tiered memory systems, the DRAM is usually used as the fast tier, and CXL memory expander and Intel Optane this PMM usually serve as the capacity tier. Both memory devices are mapped onto the same physical address space and can access memory at a cache line granularities. To extract full potential benefits of the fast tier, it is important to maximize the utilization of the fast tier with frequently accessed hot pages. To do this, the OS needs to first monitor memory accesses and determines which pages are considered hot. Then, based on hotness results, the OS should initiate page migrations. One of the important things is how hot pages is determined based on what criteria. So let's look at how previous systems do this. In most prior approaches, hotness threshold is deeply entangled in their design. For example, automatic NUMA balancing in stock Linux scans page tables and sets a protection bit to make further accesses to scanned pages trigger page ports. So if CPU access the scanned page, NUMA hint page port occurs, and AutoNUMA try to migrate ported pages to DRAM if there are some pre-space. So in other words, AutoNUMA only considers the page recency, and the hotness threshold of AutoNUMA is just 1 in this case. Recently proposed TPP enhances the AutoNUMA functionalities by decoupling allocation and demotion procedures, and by employing more apt hot page detection methods, which harnesses pages position in existing LLU lists. So if a page in the inactive list are accessed after scan, the NUMA hint page port occurs, and TPP moves this page to the active list instead of directly promoting it to fast tier. After that, if the subsequent NUMA hint page port occurs at the same page and this page is still in the active list, this page TPP promotes it to the fast tier. So we can say that the hot threshold of TPP is 2. Next example is HEMEM. HEMEM tracks memory accesses by using processor event-based sampling called PAPS. It uses 2 static thresholds. One is the hot threshold, which is set to 8 load accesses or 4 store accesses. The other is cooling threshold, which is set to 18 accesses. So any pages with access count beyond the hot threshold are directly promoted to the fast tier, and whenever the access count of any page reaches the static cooling threshold, HEMEM halves the access count of all pages to ensure the freshness of hot set. So as you may know, the quality of hot and cold page detection critically affects the effectiveness of tiered memory systems. But many recent systems still adopt static criteria for hotness detection. So our question is, are such static approaches sufficient for transparent management of shared memory. There is a diverse set of applications in modern cloud and data center environments, and new memory functionalities like CXL memory pooling it allows for even more flexibilities in memory setups. So to make the systems efficient and transparent, tiered memory management method should perform well across a diverse range of applications and memory configurations. So there are two typical cases which hamper the effective utilization of the fast-tier memory. The first case happens when the hot set size exceeds the fast-tier size. In this case, some subset of hot pages will be placed in the capacity tier. The problem is that such subset of hot pages has arbitrary hotness. It means that hot pages accessed very frequently could be placed in the capacity tier. So it highly likely to be to degrade the system performance. The second case happens when the hot set size is much lower than the capacity tier size. In this case, we can ensure that very hot pages are placed in the fast tier. However, the remainder of precious fast tier size may be wasted with arbitrary cold pages. Thus, it seems good to maintain the hot set size as close as possible to the fast tier size. Unfortunately, it is impossible with static hotness detection. So we examine actual hot-cold memory footprint by using HEMEM and two applications, PageRank and AccessBench. The black dashed line denotes the DRAM size allocated to each application. In case of PageRank, HEMEM consistently classifies 1/2 gigabyte of memory as hot, so nearly half of past tier can be underutilized with arbitrary cold pages during entire duration. In AccessBench, the hot set size initially exceeds the fast tier size for 130 seconds, then very rapidly decreases. Such a significant drop of the hot set is caused by a few number of pages which are excessively accessed and then incurs frequent cooling operations. So this results clearly show that the static criteria for hotness detection is not optimal. One can try different threshold values to get the best result for these applications. It is unlikely that a single threshold will work well across different workloads. Our solution is MEMTIS. MEMTIS enables to make the best use of the past tier with truly hot pages. There are three main design components in MEMTIS. Firstly, MEMTIS tracks memory accesses by using hardware event-based sampling techniques for scalable and fine-grained access tracking. And it maintains its CPU overhead for access tracking below a predefined threshold, so it is very lightweight. Secondly, MEMTIS harnesses the overall access frequency distribution of pages in determining page hotness. It collects distribution by using page access histogram and properly fills the past tier with very hot pages. Lastly, using a huge page is not always good to performance in tiered memory systems because not all solve pages in the huge page are evenly accessed. Thus, MEMTIS automatically balances the address translation cost and memory access cost by dynamically deciding the most appropriate page sizes. In this talk, I will introduce how MEMTIS tracks memory access and determines hot pages. MEMTIS uses paths and samples two types of events, address load miss and store instructions. We initially set the sampling interval to once every 200 for address load misses and 100,000 for storage instructions. Sampled events are recorded in a fast link buffer, and each sample contains exact memory address that a corresponding event happens. Our sampling thread, called ksampld, reads this buffer and handles a sample. It first finds a sampled physical page and updates the access counts. If this page is huge page, MEMTIS updates both the access count of huge page and the access count of the solve page inside the huge page. Note that the access information for solve pages is only used by our page size determination procedure. Then, to obtain the memory access distribution of pages, we update the page access histogram whenever we handle samples. Each bin in the histogram represents a specific range of access counts, which follows an exponential scale. So, for example, nth bin has the range of access counts from 2 to the power of n to 2 to the power of n plus 1, and the last bin has no upper bound on it. The value of each bin denotes the number of distinct pages in the access count range. Thus, we can know the total number of pages which has the specific range of access counts through this histogram. Updating page access histogram is very efficient. Whenever K-sampled updates the access count of a page, it checks whether the new access count falls into a different bucket and updated histogram if needed. K-sampled periodically calculates the exponential moving average of CPU usage and adjusts the sampling period to meet the upper limit of its CPU usage. By default, this limit is set to 3% of a single CPU time. We observed that across all our evaluated benchmarks, K-sampled only consumes roughly 2% of a single CPU time with 0.9% of performance overhead on average. MEMTIS established hot, warm, and cold threshold by using the generated histogram. And we used the bin indices as threshold in our system. Each goal is to maintain the hot set size as close as possible to the fast tier size. To determine the hotness, MEMTIS sums the total size of pages fallen into each bin in the histogram, from highest to lowest indices, like this manner. So if the cumulative size of the hot set exceeds the fast tier size, an arbitrary set of hot pages could be placed in the capacitor. So to avoid such an undesirable state, we set the hotness threshold as the bin index preceding this point, and such that the past tier can accommodate all hot pages. The number of pages fallen into this bucket is spanning both memory tiers, so we classify them as warm. The warm pages quickly transition to either hot or cold states, so we don't allow them to be promoted or demoted unless they should inevitably be demoted for securing some free space. It helps to prevent some ping-pong migration behavior like demotion right after promotion. Yeah. So it's very efficient to systems. Finally, the remaining buckets are classified as cold, and all pages belonging to these classes are placed in the capacitor. If you don't adjust the hot threshold, the hot set size will exceed the past tier size as pages are accessed and the histogram is accordingly updated. Thus, we periodically adjust the hot threshold to maintain hot set size below the fast tier size. In addition, MEMTIS performs cooling for pages and histograms to ensure the freshness of memory accesses. Our cooling process halves the access count of all pages, which is indeed calculating the exponential moving average of access counts. Moreover, since we configure the histogram exponentially, cooling requires merely shifting the value of each bin in the histogram just one bin to its left, so it is very efficient. To evaluate MEMTIS, we constructed a tiered memory system by using DRAM and Intel obtained these persistence memory modules on our Cascade Lake server. To demonstrate the effectiveness of MEMTIS, we conducted experiments with 3 distinct tiering configurations, each defined by the ratio of fast tier to capacitor sizes. These configurations included 1 to 2, 1 to 8, and 1 to 16 settings, allowing us to explore a range of memory setup scenarios and their impact on system performance. Firstly, we examined the amount of hot, warm, and cold memory identified by MEMTIS, especially focusing on 2 different applications and 2 distinct tiering configurations. Unlike HIMEM, MEMTIS adjusts the hot set size to align with changes in the fast tier sizes. So this adaptability is proved to be effective across both applications. Now we show the performance comparison to existing Turing systems. There is no one system that generally works well. TPP is doing well for Graph 500 and XSBench. It shows the worst performance in PageRank. MEMTIS performs best in almost all cases because it effectively manages the hot set, considering both memory access distribution and memory configurations. One interesting point is that even under 1/16 setting, MEMTIS shows similar performance to, or sometimes outperforms other systems like this. You can make it the performance of Autonuma in XSBench at 1/2 setting is slightly better than that of the MEMTIS. This is because in XSBench, a very skewed hot memory region is allocated at early stage. Ironically, Autonuma lacks the demotion feature, so it cannot demote the early allocated hot pages, thereby showing better performance in this case. We evaluate MEMTIS by increasing the resident set size of Graph 500 from 128 gigabytes to 690 gigabytes. In all experiments in this result, the press tier size is 64 gigabytes. Autonuma has no performance improvements in all cases. And TPP works well when the RSS is 128 gigabytes, but its effectiveness decreases as the RSS increases. This is because it tracks memory access by scanning page tables, which are not scalable to increasing memory sizes. HIMEM uses PAPs, thereby showing the consistent performance improvement and outperforming other systems if the RSS is larger than 300 gigabytes. And MEMTIS also uses PAPs and optimally classifies page hotness, thus it always shows superior performance in all cases. So this result clearly demonstrates the effectiveness of PAPs and the importance of precise hotness classification. To summarize, efficient and transparent management of tiered memory systems should track memory access in a scalable way and considers both diverse memory access patterns and memory configurations. And it needs to maintain the hot set size as close as possible to the fast tier size. MEMTIS does all these things and thereby enables efficient and transparent management of tiered memory systems. Thank you for listening. Yeah.
Thank you. And we have first question here. Please state your name and affiliation.
Hi, Shaurya Patel, UBC. Thanks for the great talk. This seems like cool work. I had a few questions about PEBs. So what I found in my experience is that PEBs generally doesn't report everything you want to know. Like it wouldn't report, let's say, hardware prefetching reads and stuff like that. So I found that the data reported by PEBs is usually much lower than you would want. So I wanted to know your experience, and also what is the sampling rate that you used?
Can you speak again slightly more slowly?
Yeah. So in my experience, what I found was that the data from PEBs is very underreported. So I was curious about your experience. How was your experience of using PEBs? And it misses some events like prefetching reads and stuff like that. And so why was PEBS enough for your case?
In my experience, PEPs is generally good to detect hot pages because it is based on the sampling techniques. But so maybe the working set size for a given time period exceeds the fast tier size. Maybe PEPs is usually good to the system because it very well in detecting hot pages. But if there are some many fast tier sizes, so if it is important to detect more cold pages, maybe PEPs is not effective. So maybe it depends on the system configuration. So,
Cool. Thank you.
yes.
Hi, Steve Hand, Google. Thanks for the talk. I have one question that's got kind of two dimensions. I have lots of applications running at the same time. Some of those applications may have different working set sizes, and some of them may be more important, to the world than other ones. Does your system sort of adapt to that? Most of the evaluations seem to take a single application and sort of have it get all the memory as fast as possible. I wasn't sure how you adjusted for effectively different value that different workloads would get from having their pages in hot versus cold memory.
It is possible to maintain the histogram for each memory secret instances, and so if there are some multiple processes, MEMTIS can handle MEMTIS can find the most appropriate hot threshold for each benchmark, considering their memory access patterns, and in some applications, it is possible to memory access patterns are dynamically fluctuate at runtime. In this case, it may be possible to some tuning in our systems, like how frequently adjust our threshold, how frequently trigger our threshold adaptation process, or how frequently performs the cooling to decay the old access, or decay the importance of old accesses.
Thank you.
Hi, Taehyung. I'm here. Okay. I'm Jiahao Li from University of Science and Technology of China. Have you read Johnny Cash published on OSDI this year? It says the sampling-based approach may perform worse when there are less profiling thread. That means when your workload they have less working thread, this method can be less working. So I wonder how's the case in MEMTIS, since MEMTIS uses a dynamic threshold rather than static ones. So if the workload, the thread number is very small, so how does MEMTIS perform?
I didn't know the details of Johnny Cash, so I don't understand.
No, this is kind of intuitive. So like the HEMEM, it uses 8xs as a hot page.
Yeah.
So if you have many threads doing work, you may identify the hot page quicker, so it can promote it quicker. But with the less thread, it doesn't reach that threshold yet. About MEMTIS, how does it perform under the low thread number?
Yes, exactly. I don't evaluate MEMTIS on low thread environments, but in my opinion, our sampling thread dynamically adjusts the PEP sampling interval. So if there are a few number of threads, maybe our sampling thread more frequently samples the PEP events. Maybe, yeah. So maybe it works well for such an environment. I think, in my opinion.
Okay, thanks.
Okay, one last question. Sorry.
Hi, Dimitrios Karlatos from CMU. Thanks for the talk. So you didn't cover that much how you use different page sizes in the talk. Like, can you describe a little bit what are the trade-offs between deciding the right page size versus migrating between the different tiers, and how do you help TLB miss rates in that case?
Okay, can you speak again more slowly?
So the question is about TLB miss rates when you're determining the page size and how the information you have available, for example, from PEBs or TLB miss rates, helps you decide how to do page migrations, or do you need something more than that?
Yeah, I proposed page migrations by using some separate color background thread, and all of the things in MEMTIS are done in the background, and whenever we try to migrate some pages, it is done by some separate thread, and when we split some page or when we collate some sub-pages into huge pages, it is also done in the server background thread in MEMTIS. So I'm not sure.
Okay, thanks.
Okay, thank you. Out of time now.
Thank you.